Welcome to Slugs and Steins Lectures from UC Santa Cruz. My name is April Yee, and I'm one of your volunteer organizers tonight. With me is Mike Reapy, a former member and past president of the UCSC Alumni Council, along with Shana Kent, executive director of the Alumni Engagement Team at UC Santa Cruz. Mike and I will stay on screen during the talk so that our speaker doesn't feel like he's alone in the room. And this talk is being recorded. It will appear in a few days on the UCSC Arts, Lectures, and Entertainment channel on YouTube. For those who are new, our Slugs and Steins series engages a UC Santa Cruz faculty member in discussion with you, our local and extended community online, with a goal of making us all Renaissance people. We want it to feel just like you're at UC Santa Cruz sitting in class, but with a drink in your hand and without tests. And even though this is a virtual event, I'd like to begin with the UCSC land acknowledgement. The land on which we gather is the unceded territory of the Awaswas-speaking Yupi tribe, the Amamutsin tribal band comprised of the descendants of indigenous people taken to missions Santa Cruz and San Juan Bautista during Spanish colonization of the Central Coast, is today working hard to restore traditional stewardship practices on these lands and heal from historical trauma. Now, since we can't see you, we'd like to know where you're zooming in from and how many people are with you. So there's a pop-up on the screen for a poll, and we'll share the results after we've given everyone a moment to respond. Okay. So you should be able to see the results of the poll and who is in the virtual room with you. Mostly just individuals watching, mainly from Santa Cruz County and the Bay Area. 2 people from outside the United States. Very cool. All right, thank you for doing that poll. So we'll be tipping our steins this evening with David Lederman, professor in physics in the physics department and the director of the Materials Science and Engineering program at UC Santa Cruz. Originally from Chile, David received his BS in physics from Stanford and his PhD in physics from UC Santa Barbara. After postdoctoral training at UC San Diego, David spent 20 years as a faculty member at West Virginia University before moving back to California to join the UC Santa Cruz faculty in 2015. David loves living in Santa Cruz and is an avid open water swimmer. So tonight, as the demand grows for electronic devices that can perform faster and store more data, the materials used to make these devices are reaching their fundamental theoretical limits of performance. And to overcome these limitations, there is a growing consensus that new materials are needed. And some of these materials have strong interactions between the electrons themselves that depend on their quantum mechanical properties, including the so-called spin of the electrons, which result in unexpected and potentially useful properties. And this evening, Professor Lederman will discuss what these interactions are, how they are related to quantum mechanics, and what are some of the potential technological applications in the context of research performed at UC Santa Cruz. And he will also describe students' involvement in the research at both the undergraduate and graduate levels, which provides them with valuable technical training for the future. As usual, we'll have a detailed Q&A at the end, but you can type your questions into the Q&A box at any time. And if there's a relevant question to be asked in the moment, we'll pause and have Professor Lederman answer it. Also, if you see someone else's question that you like, you can upvote it and we'll do our best to have it be asked and answered sooner. Okay, does everyone have their steins? Great, I've got your slug, Professor David Lederman.
Thank you so much for that kind introduction, April. I want to thank the UCSC Alumni Council for inviting me to give this talk. It's really a privilege. And anyway, we'll just get started. I am going to share my screen. One second. Okay. I'm going to share my slides. Okay, here we go. So today I'm going to tell you about quantum materials for the electronics of the future. My name is David Lederman. I'm a professor in the Department of Physics at UC Santa Cruz. I'm also the director of the Material Science and Engineering program. I'm going to tell you a little bit more about that later. We have a new graduate program in material science and engineering that's just kicked off this year. So maybe some of you might be interested in that, knowing more about that. And here's a link to my website in case you're interested in getting more information. So, so you may not realize this. I think most of you know this, but you know, there's a strong link between information and communications technology and energy use and climate change. For example, when we talk about cloud storage, you know, storing data in the cloud, it doesn't just go into the cloud and, you know, and disappear. It's not free. You know, all of this information has to be processed and it has to be stored on servers that use a tremendous amount of energy. So what I'm gonna do here is first I'm going to try and convince you that this is a problem that needs to be addressed. That this problem should be addressed with the development of new materials. And then I'm going to tell you a little bit about what I do to try and contribute even a little bit towards the solution of this problem. So in 2018, the information and communications technology accounted for about 2% of the global emissions. 2% is not nothing, you know. What does that mean? Well, there's cloud storage, that all that information has to go into computers, into servers, mobile communications. There's the industrial Internet of Things, which means that you know, computers, the use of the internet to control machinery or equipment in a factory setting, for example, and then something that wasn't really so important in 2018, although it was already emerging, is cryptocurrency, which is a huge contributor, a huge contributor to this demand for energy, and then AI, which, you know, that's super new, right? I mean, that's just happening in the last year and a half. So some of the statistics I'm going to show are already dated. I believe that everything that I'm going to say is, you know, kind of a lower bound, because AI and cryptocurrencies are starting to dominate the demands for information communications technology and energy consumption. So the models, these models, which I think are already outdated, they predicted that at least 20% of the global energy used by ICT, by the information communications technology, would be 20% of the use by 2030. That's significant, and 2030 is only 6 years away. So just to give you an idea of what we're talking about, here's a photo of a data center in Sweden owned by Facebook. And you can see that each one of these things is a server, it's a computer. These things require air conditioning. They require sometimes special water cooling because they generate so much heat that if you were to not cool the room, for example, then all the microprocessors wouldn't work the way they're supposed to. So it just uses a tremendous amount of energy, and it's inefficient, right? Because it generates a lot of heat. Okay, so that's the other thing. Here's another photo. This is a Google Center in Oregon, and you can see that they need to actually provide water cooling in order to cool the rooms and cool the servers. And here the blue pipes are cold water, then they run through the servers, and then they come back and they're hot, and then they have to be cooled somewhere using some sort of air conditioning system of some sort. Okay. So all of these things use up a tremendous amount of energy. So here's where that 20% the 20% of energy usage number comes from. This is from this paper in Nature, and you can see that depending on the models, depending on what you assume, they claim that it's 20.9% by 2030. This here this is the production of ICT, the consumer devices, the data centers. Look how the data centers are increasing in green here, and then these are the networks. But I believe this data centers is under, it's undervalued because, of the emergence of, cryptocurrency and AI, which I'm sure AI was not taken into account in this 2018 calculation. And so you can see that there's different models that talk about how much, depending on the internet traffic, depending on other things, how much you would use, but it's 20% of the electricity demand. So, I mean, that's a substantial energy use. And then compounding this thing is the fact that a lot of these applications require a significant amount of computing power, and so there's been a lot of pressure trying to make the computers more and more efficient throughout the years, and this leads me to a short discussion about what's called Moore's Law, named after Gordon Moore, who was the founder of Intel. And you can see here that Moore's law says basically that this is a logarithmic graph. So that means that a straight line means it's an exponential growth, which means here that every certain number of years, the number of transistors in an integrated circuit would double. Okay, so it doubles itself and it doubles itself, it doubles itself. Okay, so it increases exponentially. So this is the original paper. You can see it here in this link if you want to. And this is where the idea of Moore's law comes from. Now, Moore's law is not really it's not a law of science. It's not like the law of gravity or something like that, right? I mean, it's just an observation, but it's held true, I mean, look at this. This data starts in 1959, goes up to 1965. There's only 5 data points, and then they extrapolated all the way up to here. Now, there's some barriers that would limit this continual exponential growth of exponential increasing the computational power. First of all, you need and the needs have to do with the increase of computational needs in society, but there's a limit actually as to the materials and architectures. This cannot go on forever. I mean, the engineers at these companies have been extremely clever, and they've done a really good job in extending this. But it's a proven fact that this is not going to go on for too much longer. And also the energy usage, as I'll show you in a minute, is unsustainable. So here's a graph from the Intel website, that shows, again, this is a logarithmic scale of the transistors per package. Now, this doesn't include things like for example, the processor speed and the memory speed. Those things are actually plateauing, okay? But even if you look at this data here of the transistors per package, I don't know, depends how you fit it. I could have fit it like this if I was going to extrapolate from 1980 on, and you could see that there's already kind of like a little bit of a, a decrease, and this could actually, it's not going to curve downward, of course, but it could plateau very, very quickly. Okay, and that's because of the heat generated by these components. It can actually affect the performance of the device, and also, even if you don't take that into account, the fact that you have to make these things smaller and smaller creates crosstalk that at some point you just can't get rid of because of the laws of physics. So this is the computer energy in joules per year. You can see this is like 10 to the 20 joules per year scale here. This is a logarithmic graph, but you can see that the trend for this thing is to eventually plateau. Okay, and this is due to what they call market dynamics. This graph is from the Semiconductor Research Corporation, which is an organization for the semiconductor industry to kind of figure out, share information and deal with fundamental problems. So they claim that it's going to level out here. This was done in 2020. Again, AI is not included here. So who knows where this is going to plateau. I also want to just call your attention to this article that was published just yesterday in the Wall Street Journal. It talks about, the title is, "There's Not Enough Power for America's High-Tech Ambitions." And basically the point of this article is that you have to, you have all of this demand for industry for this technology, and you can't create these data centers using green energy. There's just not enough of it available. And so what this is doing, even though, say in Georgia, where they want to open up these data centers, they're very interested in using green sources of energy, renewable sources of energy. They are not going to be able to do this because of the surge in demand is so fast and so extreme. So this is a problem. It's not just a problem of conserving energy for conserving energy's sake, but also it affects things like climate change. So this is problematic. So this brings me to the focus of the material science and engineering program at UC Santa Cruz in general. And we have our website here, although this is going to change soon, but for now, this is what our website is. And the theme that we have here is the materials for a sustainable future. And we call it sustainable materials, but it's not, we're not focused so much on recycling and things like that, which is what you would think in terms of materials if I told you that's what we were doing. What we're really thinking about is what materials you use to make these electronic devices, and how you can make the electronic devices more efficient and more energy efficient, and at the same time have the same computational capabilities that you have now. So again, more energy is being used to run this information and communications technology, and we're approaching the theoretical limits even of the current electronic materials. So the point is that because of the link to climate change, if we're serious about dealing with this, and if we are going to have a significant portion of our energy being used up by these data centers, then we need to come up with fundamentally new ways of making this circuitry and making computation so that it's more efficient. So imagine that if you could do all of this computation without generating so much heat, right? I mean, if you, instead of generating that heat, you could use that energy to just compute more and use a lot less energy. So that's sort of what the idea is behind our program, the research portion of our program at UC Santa Cruz. And I think that fits very well for those of you that are alumni. It fits very well with kind of the general theme at UC Santa Cruz, which is to, do good, I think, overall, and think outside the box. Okay, so now what I want to do is I'm going to tell you a little bit about the research that I do, and tell you. I'm going to give you an overview of the objectives of what we do in my lab, and then I'm going to show you some technical stuff. I'm going to try and make it as accessible as possible, and give you a flavor of what it is to do research in this field. Okay, you might be surprised. You might be surprised to know that we actually do a lot of hands-on work here. It's not quite engineering, but it is fundamental physics work, fundamental materials work, and we do work with our hands. It's not all theory. A lot of people think that in physics everybody's a theorist person and we just sit here and we calculate things all day, but that's not true. Okay, so anyway, so the idea here, our goal is to create new functionalities of stacks of different materials that will result in efficient, in low power electronics that can be used to mitigate the problems I just talked about. And our goal, our fundamental goal, our goal is to understand the properties of these interfaces. And I just want to make sure that I'm very clear. We don't make the devices ourselves. What I call a device is not something you would want to put in your computer or your car, okay? Because it's not that reliable. It works once, basically. Okay, so it's a completely different thing. It's fundamental research, but the idea is to provide knowledge that will later could be used could be implemented in a real device in the future. So to illustrate this, here's a painting by Linda Cover, and it's hanging in my lab. And what it is, it illustrates what the research in my lab is about. So what you do is you make two materials, say A and B. So you have the apples and the bananas, right? And they symbolize two different types of materials like this. And then what happens is when these materials are very, very thin, you see there's only like a couple of layers of apples or a couple of layers of bananas. So that's kind of like a couple of atomic layers, maybe just a few. Okay, you can think of it that way. And you can see that at the interface here between these two things, you have a new material that's created, material C. This interface stuff here has its own properties. And because these two layers are very thin, this interface can actually dominate the physical characteristics of the material. So it's like you're making something new out of two materials that you're making something completely new. And that's what we're trying to do. And you can see that there's all kinds of symbolism here. For example, you can see the cat here. This one's alive and this one's dead. See that? That symbolizes Schrodinger's cat, right? So it's the importance of quantum mechanics. And then you have these yellow things are compasses. That symbolizes that my interest in magnetism. Okay, so magnetism is very important here. And you can couple magnetic things to things that are not magnetic normally and make them not magnetic. So you can do all kinds of neat things. And then these lightning bolts symbolize that you can control things with electricity. Okay, so that's a really nice painting, and you can learn more about Linda going to her website. And this was, just as an aside, this was pre-COVID. Okay, it seems like ages ago, decades, but it was only 2019, and we had at the time we had a fusion. We called it science fusion art exhibit, and so a lot of the physics department faculty and astronomy also, they teamed up with local artists, and we had an exhibition here in Santa Cruz, and it was really neat. And so you can go to this website and you'll see some of the photos of some of the other work that was done there, but it's really neat. But anyway, I got this thing hanging in my lab, and it always reminds me of what we're trying to do, you know. And so that's the one of the objectives, but we have a second objective that is also very important. We are a publicly funded university by the state of California and by the federal government. And so, you know, one of the important missions of the University of California is research. I mean, that's, you know, we are supposed to do research. It's one of our stated missions of the University of California, but we're also supposed to educate and provide workforce training development for our students. And so that's another mission that we do here. We educate and train our students and postdocs as well, but postdoc is somebody that already has their PhD degree, and then they get additional experience, more independent type research. And the neat thing that we have available, that we provide for our students, is that the same techniques that we use in our labs are used in industry as well. Like the semiconductor industry uses the same techniques to make materials and to characterize them and to measure them. And so our students come out of this thing, and they're not like, you can get a PhD, a master's degree or a PhD in our program, and it's not just, you know, it's not just good for going into academia, but you know, you will be trained, you will have experiential knowledge of how to do this in an industrial setting as well. Actually, it would probably be easier in an industrial setting because our stuff is all kind of like home built, you know. So they get really, really good education. Okay, so that's the other mission, and I'm going to talk about both things in some detail. Before I do that, however, let me show you where our lab is located. We are not located on the main campus, as it turns out. So here's a Google Maps aerial photo of where we are. And you can see, I guess it's a satellite photo, and you can see that here's Natural Bridges State Beach. Here's the Marine Discovery Center, the UCSC Marine Discovery Center. If you're familiar, here's the farmers market that meets every Saturday here off of Mission Street on the west side. And UCSC, the main campus, is up here, but we're located right here. This is our building. It's actually, the building looks small here, but it's actually huge. As it turns out, this used to be a Texas Instrument fab many years ago. It was sold to UCSC. It was actually very, I mean, it was basically given to UCSC, and now UCSC has been building new labs here from the School of Engineering and Physics, and so we're very excited about this, what's going on right now. We have several projects, construction projects going on as we speak. Here's a photo looking south, so looking down this way, and you can see here's the building, here's Antonelli Pond, and you can see in the background, you can see the Monterey Peninsula over here. So it's really a fantastic place to work. You know, you can just cross the street and go to Natural Bridges Beach. It's literally like a 5-minute walk. It's really fantastic. Now, what is it that we actually do in the lab? So, you know, I mean, we actually, again, we have a lab. Most people think that labs are for chemists or biologists or whatever, but we physicists and, you know, we also have labs. So I'll show you what we do. This is one of our equipment it's sitting in a clean room, and this is a molecular beam epitaxy system. And what it is you have a bunch of chambers. These things are in vacuum, so there's a very low pressure inside of them. They're stainless steel. These things are made of stainless steel so that the pressure, from the air doesn't just crush them. And then what we do is we just heat things up in the vacuum, and then we collect them on a crystal, and that's basically what molecular beam epitaxy is, and then there's some things you have to match the structure of the crystal to the thing that you're trying to grow, so that the thing grows really, really well as a single, crystal, and it's not just a mixture of stuff. And we can do characterization inside the chamber as well, so we know what we're doing. And usually these layers are very thin, so they can be like 10 atomic layers or even fewer. So then what we do after that, after we make our material, is we characterize it, because we need to know what it is that we've done. And I'm a little bit of a paranoid person, and I never trust myself. And so I what they say, trust but verify. I think we had a famous president that used to say that, right? And so this is what we do. We have various tools that we use to verify what we've made. So we have X-ray diffraction. Things are very thin. You can't see them with a regular optical microscope. So we use X-rays to figure out what the structure is, where the atoms are sitting. We do extensive magnetometry. This is what's called a superconducting quantum interference device. It's a squid magnetometer, and it's like the most sensitive type of magnetometer that you can have. So we can measure if something's magnetic, we'll see it, even if it's very thin. And we do microscopy. This is an atomic force microscope. So this is not optical microscopy like you would see under a microscope with your eyes. You have a tip, and it scans this thing, and because things are so small, you can't use the wavelength of light to see them. And these arms are actually, there's nobody in there, don't worry, okay? What it is like, there's actually, this is inside a glove box, and it's over pressurized. So these are like plastic arms, and they come out. But normally somebody would come in and stick their hands in there and manipulate their samples through these holes, okay? It looks goofy like this, but yeah, there's nobody inside. Okay, so, and then after you've characterized your sample and you're satisfied that you know what you have, then you want to make a device, okay? Device in quotations, okay? I should have put the quotations here, because again, it's not something that you would normally think of like you could buy at the store and, have it guaranteed to work every single time, right? So what we do is we do all kinds, we can do photolithography. We can do another technique called electron beam lithography to make really, really small patterns. And then after that, after we made our device, we put it in what we call a cryostat, because what we want to do is really study the fundamental properties of these things. And so we want to measure things at very, very low temperatures, so we can get rid of all kinds of things that can affect the signal that we're really interested in understanding. For example, the atoms, tend to vibrate at high temperatures, and those things can affect the way the electrons move around. And so we want to get rid of those vibrations, and to do that, we cool it down to like really close to absolute zero. And then we can apply very high magnetic fields in this thing. And we measure the conductivity, basically, as a function of magnetic field and temperature if we have to. So just to show you what our devices look like, look at this. So this is, again, looks very clunky, right? But what it is, it's like my student made a sample in here, and then he used photolithography to make something a channel that makes an L like this. And you see here, these are contacts using silver paint. So we have other ways. We have a wire bonder too, but he didn't like using wire bonding because this material is actually very, very delicate. So he used this, he had to go in a microscope and put a little dab of like this little paint, conductive paint, and then connect these wires to this chip holder here. So we buy the chip holders. And then what's interesting about this, my student was very clever. He wanted to measure the sample with a magnetic field pointing in a certain direction. So to do that, he 3D printed this red piece here that looks like a wedge here. The sample sitting actually, the photo from the bottom was taken from the left. So it's sitting upwards, upright like that. So he had a friend of his make it. I don't know who the friend is, but they made it like this, and then he mounted it like this, and then this is a real labor of love. I mean, this is not easy, to mount the sample and then put the wires by hand and all these things, because this is very, very tiny. I mean, here it looks big, but it's actually, from here to here, it's only like 3 millimeters, so it's quite small. So anyway, he did a really good job, and he made several of these devices like this. Devices, right? Okay. But you can see how this has these pins here. We have a connection at the end of our cryostat. We put it in here, and then we stick it down there, and it gets really cold. And then we measure things. So that's what we do. And again, the research goals, just to remind you, are that, we want to find new materials. And we're going to rely on quantum properties. And for that, we're going to use what's called spintronics, the concept of spintronics, which is to use the spin of the electron to transmit information. So instead of using pure electrical currents that are an electrical current means that the electrons have to get from point A to point B, basically. And as they travel, they scatter off of things, and then they lose energy as heat. That's what causes heating in these servers and all of these things, okay? So instead of using the electron movement, we actually excite the spin of the electron, and it's this excitation that moves around, okay? And the other thing we're going to do is the use of what are called topological properties of the wave function to enhance spintronics. Don't worry too much about this, what this means. Let's just say that what we're doing is that when you combine spintronics with these properties of these types of topological materials, you can get an enhancement of the effect. So that's what we're going to try. That's what we're going to try and do. So there's a couple of concepts that we use here. One is what's called the exchange interaction between electrons. And the only reason I'm mentioning this is because you may have wondered why, you have magnetic materials and you have non-magnetic materials, like iron is magnetic, right? Everybody knows that if you put some sort of iron oxide, you can get like a bar magnet, or you can get your refrigerator magnet, right? But then there's materials like aluminum. Aluminum is not ferromagnetic, right? It's not going to be attracted to a magnet, right? So that's because of the interactions between the electrons themselves. There's an so-called exchange interaction that can cause things to align between neighboring atoms, for example. They can align parallel to or anti-parallel to each other, depending on the case. If it's anti-parallel, then it's not magnetic, but it's got magnetic order. If they're parallel, then you have a ferromagnet. That's what you're used to, okay? I'm going to talk about this kind of arrangement where they alternate up and down, and then up and down, etc. I'll discuss that in a minute. When you combine this with these new topological materials, which these things came about, this concept relatively recently, less than 20 years ago, so it was past 2000. Then you can get all kinds of interesting physics that you can study and interesting applications. One of them is that, in principle, you can have dissipationless charge and spin currents. That means that they don't scatter very much, so they generate less heat, right? More efficient electronics, which is our goal. So that's why we were interested. We want to put a magnetic insulator near a topological insulator, for example. This material is really an insulator. It doesn't conduct electricity. This one is called a topological insulator, but what it means is that it doesn't conduct electricity inside, but it does conduct at the interface, okay? And the two, when they interact, you get this kind of dissipationless motion, which is really what we're after. look how this looks a lot like this. You see that? This is A, this is B, and this is C. A, B, and C. So you're creating something in the middle that has its own properties. So it fits really well with what Linda covers diagram of what we're trying to do, right? So what we want to do is we want to use an antiferromagnet to do this. There's other interest, not just because of the energy efficiency, but you can also transfer information very, very fast at the terahertz rates instead of gigahertz, which is the more common frequency range. It's like 1,000 times faster. Okay, so that would also save energy. Okay, so I just want to tell you, okay, this is what the spin of an electron looks like. Actually, it doesn't look like this. This is just a diagram. Okay, there is no. It turns out that electrons, you can think of them as having a north and a south pole. They're like magnets on their own by themselves, because that's the way it is. Okay, it's a fundamental property of these particles, electrons. Okay, and so in an antiferro, you can have a ferromagnet where the electrons that are near one side coupled to the other ones, and they all point in the same direction. This is called a ferromagnet, and that's what you have for like your bar magnets and your refrigerator magnets. And then you can also have an antiferromagnet, however, where the interactions between them cause these things to alternate up and down. This one doesn't, right? If you add the plus, if this is +1 and this is -1, if you add, you get 0. So you would think this is completely useless. It has no net magnetization. But it turns out that that's not true, okay? I'll show you an example of that. So these are some of the applications that you can have with antiferromagnets. That's not too important, but what is important is the following. One thing that you have to realize is that spins are not static. You can have these spins can actually rotate like this, and they spin, or the spins themselves can cant in a certain direction, and then they can precess, kind of like a top. When you have a top, it precesses around as it leans over. But because you have two of them, you can actually have a mode where this thing precesses this way and this one precesses in the opposite direction. And you can have this mode here where this one precesses this way, like clockwise instead of counterclockwise, and this one precesses counterclockwise. So they can flip over like that. You have two different, what are called chiralities. So the question is, can you use this for anything useful? Like, can you somehow figure out whether this thing is rotating by measuring a voltage? At the end of the day, you have to measure a voltage, because that's what electronics uses. So even if you can transmit information with spins, at some point you have to translate it. You have to transduce it to something, a voltage. So that's what we aim to do. We take an antiferromagnet, and what we can do is we can run a current through a material that has a lot of protons, like platinum or tantalum. These are heavy elements. They have a lot of protons. You run a current. This thing generates as the spins start precessing, and then you can detect them by using another layer, using the inverse effect. This is called the spin Hall effect. Don't worry too much about the names, okay? But the point is, if you have this thing that's heavy, you run a current, you can generate like this precession, and then this precession just travels around, kind of like a domino, a stack of dominoes when they fall on top of each other. You can see where the falling happens, but the dominoes don't move very far, right? It's the same thing here. Like sound waves, right? It's the same thing, okay? So you use the inverse effect for detection. Okay, so let me show you a very, very great experiment that we did. What we did here is we want to show you proof of principle that this was actually possible. So what we did is we grew a film of manganese difluoride. This is an antiferromagnet, okay? And it's got these two sublattices, and you can see how they would precess like this, as I showed you earlier. And then we put platinum right next to it. what we did is we excited a wave by irradiating it with a radiation that was resonant with this. So it's pushed the things around using radiation, using electromagnetic waves. And then the question was, can we detect that voltage in the platinum? Because if we can prove that, then that opens up the door to say, okay, this is not just a theoretical thing, but we can actually do this, you know? And sure enough, we were able to see this. I want to show you this graph. This is from our publication from 2020, collaboration with Enrique del Barco's group from University of Central Florida. This is what these signals look like. This is the voltage as a function of magnetic field. And the magnetic field basically tunes the resonance. And once you hit the resonance, when this thing really wants to process, you can see this dip here in this black signal here. And that's what we were looking for. In real physics experiments, this is what things look like. Okay? We look at little tiny signals that look like this, and then we say, you know, eureka, right? Kind of. Okay? And sometimes in a lot of these discoveries, you know, you start out with a really small signal, but then you can, once you understand what's going on, you can make things better, and then the signal gets a lot better. So this is what we did in 2020. I want to show you some other things here. This is a simulation of what happens as you increase the magnetic field. When you hit the resonant frequency, then the spins start processing like this. And when that happens, you see a voltage in the platinum, okay? And the signal that I showed you here, they were also able to measure the absorption as well. So that verified that, in fact, yes, we were exciting that mode. And in addition, you saw the voltage at the same place, which is exactly what you expected, okay? And there were all kinds of different modes that we could look at depending on the magnetic field. I'm not going to bore you with all of these things, but one thing that you always want to check. So this is just to show you how these things work. These experiments are really hard, and you always want to check that you're not fooling yourself. I think Richard Feynman was the one that said that the easiest person to fool is yourself. You know, you can fool yourself because you're of course you're predisposed and you want to be positive all the time, most of the time, right? And so you think you've discovered something, and most of the time nothing. It's just some artifact or something. So one of the things that you want to check is, for example, as you change, they could change the polarization of the radiation from going left circular to right circular. So the magnetic field rotates in one direction with time, and then the other direction with time, and that should have changed the position of the field at which you observe this from positive to negative fields like this, and it shouldn't appear on the other side. And that's exactly what we saw. I mean, this is theoretically predicted, you know. So we wanted to check this because there's all kinds of things that could have caused this thing. So we were worried about this, and they checked the other side as well. So these are two different modes. This one's at 336 gigahertz, this 240 gigahertz. So just to give you an idea, you know, your cell phone operates at like 4 or 5 gigahertz. So this is significantly higher frequency. So this was very exciting. Now, I want to tell you about another experiment that we did. So this is my student, Ryan Van Haren. He actually just graduated, and we miss him very much. Actually, I miss him. I don't know. Haven't asked the others, but I miss him. And so basically what he did is, he's the one that made those devices that I showed you earlier, okay? And then he grew different samples like this. This is a topological insulator and a non-magnetic material. And then here he'd do the same thing, but with an antiferromagnet in between. So the non-magnetic is not magnetic, shouldn't do anything. So this is kind of like a control sample. This is the magnetic sample, and we want to see if there was a difference, because we wanted to check whether there's coupling between these two materials. You know, and if you remember, this is what we have here. Topological insulator, antiferromagnet. Is there coupling in the middle? Can we have some property of the interface that we can exploit? But the first thing you have to show is whether there's any coupling. You know, because sometimes it's not obvious that that's going to happen. if you know chemistry, it depends on how the orbitals are, oriented and stuff, and there could be no coupling. You just don't know, okay? It's hard to calculate these things from just first principles. So you actually have to do the experiment. I'm not going to tell you too much about the details, but we figured out how to grow this thing really, really well. Okay, very crystalline and smooth, which was very difficult, actually. It took several years to figure that out. How do we know that we have something that's crystalline and smooth? Well, this is what the X-ray diffraction diagrams look like. Don't worry about I'm not going to bother you with all the details, but it showed that it was growing in one direction, that it was crystalline. Okay, and I just want to show you what the data look like. I mean, this is not simple stuff. You just have to kind of like know a lot to be able to interpret these things. But he knew a lot, and now he's gone. Okay, no, anyway, he's not gone forever, hopefully. Anyway, so here's what the data look like. You see what happens here? This is the conductivity as a function of magnetic field taken at 2 Kelvin. Okay, so very, very close to 0 Kelvin. And you can see that the sample that was grown with the antiferromagnet had a much smaller effect, like a factor of 10 smaller than this one. Even though these materials are actually very, very similar, it turns out that just putting this layer here just kind of killed this effect, And we believe that that's because of the magnetism playing a role into these topological states here, and it really disrupts them, and it shows that there's coupling. So you can read more about this here in this paper on arXiv. That's actually, I think we just got the reviews back from the referees, and I think it's going to get published very soon. Okay. The way this works is you have to submit it for review, and then it gets reviewed by some anonymous referees, and then they give you many questions that you have to answer. But we believe the reviewers were disposed, they just wanted us to answer some really hard questions, but we can do that. Okay, so I want to end the talk by going back to the mission number 2 of our lab, which is about workforce development and education. I want to tell you a little bit about this, our material science and engineering program. It's a new program. It's got about 25 faculty involved. We have at least six faculty that have joined us in the last 5 years. These are growth positions that the university invested in to accelerate our efforts in this field. And if I had time, I would tell you a lot more about the research from the other faculty members. We have a new material science and engineering graduate program, doctoral and master's level. We just admitted our new class, our inaugural class, and we're starting in the fall. It's really going to be a great program. We were the only UC without a material science and engineering program, as it turns out. But now we have it. It took us about 7 years to get this done, because it has to be approved at many different levels, and finally we were approved last year by the University of California Office of the President, which was the last step. It took a long time, but we have lots of support here at UCSC, and so I'm very happy that this finally got done. And as part of this program we've had for several years, for the last 7 years, we've had a research experiences for undergraduates program, where we have about 10 to 12 students working in the summer at UC Santa Cruz. We're especially interested in attracting students from community colleges and non-PhD granting institutions to give them an opportunity to do research at a high level, because these are students that normally would not have that opportunity. They're very, very smart. They're very talented, but they normally would not have the opportunity to get experience like that. So we try to provide them that. We also have students from UCSC and other R1 research intensive institutions. So they're not all from community colleges, because we want the students to interact, with other types of students as well. I think it's been a very successful program. We've had some students that have done really, really well. For example, this student that worked in my lab, she just got awarded a graduate research fellowship by the National Science Foundation. So unfortunately, she's not coming to UCSC. She's going somewhere else. But we've had several of these students that have actually ended up being in our graduate, that have migrated to our graduate programs. It's a great way to actually recruit students for UCSC, graduate students for UCSC as well. And the other thing that we have partnerships with, industry in Silicon Valley. We are the UC campus that's actually closest, geographically speaking, to Silicon Valley. And we also have 3 national labs within driving distance, Lawrence Berkeley Lab, we have SLAC, and Lawrence Livermore National Labs, all of which we work with, especially LBNL and SLAC. And of course, we have the new UCSC Silicon Valley Extension in Santa Clara, which we intend to, as a program, to work with more closely as well. So we're very excited about our new material science program. And finally, I just want to thank our team members, especially at UCSC. Sophie Morley was a postdoc for a couple of years, more than 2.5 years, and she's now a staff scientist at Lawrence Berkeley Lab. Ryan Van Haren, who actually just got a job at the University of Maryland, so he'll be starting his postdoc very soon. And Becker Sharif, who's currently a student in my lab. And then the people at the University of Central Florida and the National High Magnetic Field Lab, which some of the data that I showed you were obtained there, and then Ran Cheng's group and Aaron Bratas, who are the theorists that we collaborate with. And you should know where the money comes from. It doesn't grow on trees. And we get funding from the Air Force, the National Science Foundation. We have funding from the University of California Office of the President. We had a multi-campus award that was very helpful. And we've had 2 Army Research Office grants for some of our equipment, totaling $1.2 million. So that was significant. So anyway, I'd be happy to answer any questions that you may have, and thank you for your attention.
Yeah, thank you, Professor Lederman. And thanks for the introduction earlier, April. My name is Mike Greepy. I just want to remind the audience, now's the time to ask your questions. You can type your questions in the Q&A box at the bottom of the screen, and April and I will ask those for you. I guess I'll start with one of my own. Maybe I'll leave the more technical questions for the audience members, but I'm curious, like if any of our audience members, if them or their students or their children are interested in going into this field, like what would you study in high school and first few years of undergrad to get into your lab?
Yeah, so I think I can't overestimate the importance of taking math in high school. Math is very important for this field. If you're comfortable with the math, then it's one thing that you don't have to worry about too much. At the end of the day, we don't do like super complicated math in our labs, but you have to have a good sense of what's going on and where the numbers come from and so forth. So in high school, especially, it's important to have a strong math background. And then in college, I mean, physics is good, chemistry is good, material science is good, even, well, engineering, of course, because our material science program here will, one of the things we wanted to get it started is because material science has become so interdisciplinary in the last 30, 40 years. Material science used to be called metallurgy back in the 50s and 60s, but now it's called material science, and it's super interdisciplinary. And so what this material science program does is it allows you to apply to UCSC, even if you're like a mechanical engineer or you have a major in material science, or you're a chemical engineer and you're interested in going this, because we might not have chemical engineering or mechanical engineering, or we might not have those majors, but you can still come to the material science program because we're interested in doing this interdisciplinary research. And I mean, and so, yeah, it's important to have a good mathematical background in high school, and then in college, just do the best you can and major in some science, physics, chemistry, engineering, earth and planetary science. You know, we have the EPS department here. They do a lot of, there's people that do material science there too, you know. I mean, they don't call it material science, but that's what they do. You know, you have rocks, you want to know what they're made out of, right? And how they got there. I mean, this is crazy, but I collaborated with some people from Earth and Planetary Sciences. And then there's a paper with my name on it in Nature Astronomy. I never thought I'd have a paper in in an astronomy journal. I mean, I love astronomy, but that's not my area of expertise, you know. And we were interested in figuring out these meteorites, what was in them, and whether they could have contributed to the formation of the atmosphere on Earth and other planets. So, you know, it was a very fundamental work, and I helped them do some experiments, some measurements, and so very, very exciting. So we do all this kind of like interdisciplinary stuff that you never know where it's going to go.
I was surprised to hear that Santa Cruz didn't have a new material science. Was it a grad program until like this fall?
Yes.
And it was the only UC. Even Merced has that.
Yes.
Wow. What do you know why it took so long to establish that?
I'm not sure. I think part of it has to do with the fact that the engineering school at UCSC is relatively new. I mean, as you know, I think it was founded in like the 1970s, right? I mean, UCSC was founded, I think, in 1965, but the School of Engineering wasn't really founded until like the mid 70s. So it's relatively new, and a lot of these material science programs in most places are they're either a department inside the School of Engineering, or it's a program, but also inside the School of Engineering. But because the school is so new, they didn't set it up that way. UCSC is a little bit more focused on data science, and you know, and so I think that created a little bit of a difficulty there, you know. But then, so here at UCSC, the primary driver is the Physical Sciences Division, PBSci, but we do get support from the School of Engineering too. So we're truly interdisciplinary in that sense. So we're a little bit different than other material science departments. But I think that's why. I think it's just the School of Engineering was just a late coming into the game here at UCSC. And when I came here, I got hired to kind of get this thing jump started, you know, and they had been discussing this for like 20 years before I got here, but they couldn't, you know, there wasn't really a framework on how to do this, you know. So, but it finally got done, and we're very excited. There's going to be an adjustment period. I'm sure there's going to be some growing pains and stuff, but I think there's a lot of interest, you know, with us being so close to Silicon Valley, and there's a big demand for people that know about this stuff.
Yeah, that is really exciting. I'm glad you shared that with us.
Yeah, thank you.
Yeah, and I wonder what are interdisciplinary opportunities you have, all the work in biology and genetics and genomics.
Yeah. There's lots of that going on here in the bio. They have the biomedical engineering program, which is pretty interdisciplinary as well. So it's kind of the wave of the future, you know. Sometimes you go to the physics department, and then you go to a chemistry department or engineering, and you can't tell the difference, you know. And they were all working on the same thing.
Yeah, we have a Oh, we have a question. I was getting worried that the Q&A box wasn't working, but maybe we've lost the audience. Lynn would like to know how big a sample you can grow in your MBE or molecular beam epitaxy machine. 5 by 5 millimeters, square millimeters?
We can grow 10 by 10, usually 10 by 10 millimeters is our standard size. Yeah.
Well, now's my chance for a technical question. I've always, I've heard people talk about electron spin before, but I've never understood the sort of analogy. I know it's an analogy with spin, but like what is the phenomenon, and what are the measurable effects? Like how can we understand what spin means?
Yeah, so the way to think about spin is that so that gets back to the question of we can ask a question, where do magnetic fields come from, right? And if you take like electricity and magnetism, the fundamental stuff, then what they tell you is that when you have a current going around a loop, that creates a magnetic field. That's called a magnetic dipole, right? And so the field lines, if you have the loop like this, then the field lines go up and then they curl back around. So that creates a current, creates a magnetic field. And if you have a loop, it's what's called a magnetic dipole. The thing is that electrons are like a current loop, and they have their own magnetic field like that. That's why it's called a spin, because people initially thought maybe the electron was spinning around, and because it's got a negative charge, it's like having a current flowing around that creates a magnetic field. You see what I'm saying? And so that's why it's called a spin, but but now we know that electrons, well, we think electrons are point particles, so they're not really spinning at all. It's just called spin, but it's really a way of saying you have this particle that acts like a magnetic dipole, like a bar magnet, essentially. And that's the way to think about it. It's not like nothing is spinning.
It's just sort of explaining it's explaining the effect mathematically, but there's no you don't really know the electron itself, like
Yeah, no, I mean, where does spin come from? That's now then you have to talk to a particle physicist. It's not a simple answer.
Yeah.
But it is a purely relativistic effect. That's known. Like without relativity, like there's something called the Schrodinger equation, which is the equation that governs quantum mechanics. But that's the equation that governs quantum mechanics in the non-relativistic regime, like in the when things are moving slow. But there you have to add the spin interaction kind of from the outside. You have to throw it in there. It doesn't tell you where it's coming from. But then if you look at another equation called the Dirac equation, which is the relativistic equation of the Schrodinger equation. It's kind of like this one is valid when things are moving very fast. If you do that, then the spin falls out of the equation immediately, as it turns out. So you don't have to add it there. It's there from the very beginning. And so we know that it's a purely relativistic effect in some way. And yeah, for various other reasons, it's actually not super surprising, but that's the best I can do, And there's other particles that have spin, like the neutron has spin,
Well, thanks for answering that technical question. We have a few questions in the Q&A box now. The first one is from Sachin. We have been using silicon for almost 50 years for computing. What do you see as a future beyond silicon in classical computing as a material of choice? Graphene? What are your thoughts?
Yeah, I mean, graphene is an option. There's people that are thinking about, again, using completely different materials. I mean, I think this is a good question because it talks about computing beyond silicon, classical computing. Yeah. So they're not referring to quantum computing, which is a completely different thing. But there's other configurations, like there's people that are talking about neuromorphic computing, which is not quantum computing. It's a different way of, and that requires different types of materials. That's another option. I think using different, again, using spintronics to transmit information and store, I mean, right now, well, spintronics is used to store information, and there are devices where you use some elements of spintronics, but using only the spin degree of freedom to transmit information is something that I think people are interested in.
Yeah, thank you. And now that we've got more than one question in the Q&A box, we can remind everybody, you can help us decide what order to ask them in. Just click the thumbs up button to upvote, and we'll ask the more higher ranked questions first. So a question from Maximo. In the sandwich structure that you showed in your slide earlier, why was an anti-ferromagnetic material chosen to be in the middle rather than a ferromagnetic material?
Well, that's an excellent question. I think the point is, when you have a ferromagnetic material, the ferromagnet has a net magnetic moment associated with it, and that can interfere. You can get other interactions, like you can have a dipole-dipole interaction, which is long range, because this thing actually is magnetized, right? And it can really make things complicate things a lot. You can have elements of one ferromagnetic region interact with another ferromagnetic region, just like two magnets, they attract each other or they repel each other. You know, that makes things very complicated. What's nice about the antiferromagnet is that its net magnetization is almost zero, so you can have different regions where you can make devices and they're not going to interact with each other. And so you can make things smaller, for example. They can get really close to each other and not worry about having interactions between them. So that's one big advantage. In addition to the fact that it simplifies the whole analysis, because you have one less thing that you don't have to worry about in an experiment. But from a practical point of view, it's actually quite important to have the antiferromagnet there. But another reason is, again, the excitations in antiferromagnets in general are much higher frequency, like in the terahertz. So you can modulate things at much higher rates and make it more efficient that way by transmitting more information per unit second, you know, using an antiferromagnet. A ferromagnet, the excitations are actually in the gigahertz range for all reasons that I didn't quite discuss, but it's true.
All right, thank you. Andrew has a question. The applications you discussed seem to be focused on computer engineering or information technology. Do you work with industry or the computer engineering department, or is this work too far from existing devices? Do you work on device heat dissipation, which seems like the other side of the problem?
Yeah, I think one of the goals that we have is to minimize heat dissipation, right? I mean, by making this more efficient. But we do have some like what I talked about today is extremely fundamental. So we're not working necessarily with industry right now, but we do have other projects where we are working with industry. We have a project where we just wrote an STTR proposal to NSF, where we're going to collaborate with that company to try to make a new device, magnetoelectronic device. It's not exactly on what I talked about, but we're always interested in working with industry and with computer engineering. I'm trying to actually, in general, we're trying to build bridges with them. We have some contacts in applied materials and IBM. And so we want to expand that. We don't want, I mean, what I showed you, again, is very fundamental, but not everything that we're doing is super fundamental like that. And this is something that we're trying to, you know, work on teaming up with industry. It's something that I think would be good for us, for our research, and it would be good for our students.
Okay, thanks. Maybe I'll ask one more question of my own. I'm kind of curious. It must have taken a lot of time and energy to assemble that lab that you have there. I'm wondering, like, how you build a lab with so much equipment. Like, do you work with industry partners? Do they donate that equipment? Do you order it on Amazon?
Yeah, that's a long story, you know. I mean, when I came here, they hadn't even started building the labs because the building is gigantic, and it was basically the labs were like all like old clean room spaces that Texas Instruments had left behind. So when they built the lab and the new clean room, they basically demolished all the old stuff. And then they built the new labs. And it wasn't just for me, they built the lab for my colleague Jairo Velasco, who came at the same time. And later on, now they built a couple other labs for 2 new additional faculty members. But that took, building those labs, the initial labs took about 1.5 years. So things move relatively slowly, actually. It takes a long time to build these labs. And then the equipment, the equipment that the MBE system, for example, that I had to, is something I brought from West Virginia that I had built over like a span of over 10, 15 years using several research grants, primarily from NSF and from the Office of Naval Research. We built that over many years. I brought it here. Then when I came here, I purchased new equipment from. One thing you have to understand, this equipment, it's not like you can order it and it'll show up the next day. These things are very specialized. It's not even like buying a car. You know, you go to the lot and you drive off with it. You know, that's not how it works. They have to make it for you. You know, so for example, the X-ray diffractometer, which is a brand new, again, you know, we had it was delivered in like October of last year. This thing, fantastic machine, took 2 years for it to get delivered. You know, they had to build it from scratch because these companies, you know, they don't like have these things for sale, and everybody, they're so specialized that everybody wants something different, you know. So it's a very slow process, you know. I mean, you know, if people from companies want to donate some, again, we use the same equipment that we use in industry, the lithography, the e-beam lithography, the transport measurements, all these things, we do use the exact same techniques, you know, and I'm always looking for used equipment that we can install in our clean room, you know. That's always something I'm looking for. But aside from that, most of the time, it's like when you buy something new, especially, it's a huge process. First of all, it takes like 1 year to get a grant funded. Even after you write the proposal, it takes like 8, 9 months before they tell you whether you got it or not, and then it takes another year or 2 for them to deliver it. So it's like it's hard.
I had a similar question. Do the way that technology advancements in the industry, the way they change so quickly, does that affect what kind of equipment you can use to like measure things or create things? And so like what you said, the process takes so long. By the time you actually get the machine, is it outdated by that time?
Oh, yeah, I think a lot of the techniques, like like the synthesis, material synthesis and characterization, that stuff improves, but it's not like these quantum things where, you know, all of a sudden you discover a new material and everybody starts using a new material. The techniques for kind of synthesizing and characterizing these things don't change as fast.
Mm.
So it's not a huge concern. You know, so it's not like I mean, it's not like computers. I guess computers have, right? I mean, it's not like it becomes obsolete like 2 years. I have equipment
Mhm.
that I've been using for 25 years and it
Mm.
still works. Keep, you know. Knock on wood. Because when these things die, they really, it really causes a big problem sometimes, right? Because
Mhm.
the company no longer exists or whatever. But the techniques haven't changed that much. There's some improvement, but it's not like things become obsolete super fast,
Yeah, got it. Thank you.
Yeah, thank you very much. This has been fun. I think I have a better understanding just sort of how like big science works at the university. So that was an unexpected piece of your talk. But I think we'll wrap up. So I just want to thank everybody again. My name is Mike Reapy. I'm a past president of the UC Santa Cruz Alumni Association, one of the volunteer organizers of the Slugs and Steins lecture series. Everybody can join me in some virtual applause for Professor Lederman. So thank you, Professor, for sharing your research with us. We often get this question. I want to remind everybody that this talk was being recorded. It will appear in a few days on the UCSC Arts, Lectures, and Entertainment channel on YouTube. And you'll, if you registered, you'll get a follow-up email with that link in a few days. Also, please consider making a donation to support the Lederman Lab. They have a lot of expensive equipment they need and a lot of undergraduates to support. Again, the lab seeks to understand the fundamental properties of materials in reduced dimensions, and they train graduate and undergraduate students of diverse backgrounds to do that work. And they could definitely use your support. We like to pay undergraduate research assistants and give them stipends and scholarships. So I'd also like to thank the staff of the Alumni Relations and Special Events offices who organized this webinar. Thank you to Shana, Diana, Paulina, Nicole, and Kristen. Also, hello to David Hansen, Julia Doloff, and Anna Gurujan, who are co-organizers of this series. You'll see some of them in the next talk. Our next Slugs and Steins lecture will be Monday evening, June 10th, with Professor of Earth and Marine Sciences, Noah Finnegan. His lecture will be on the impact of wildfire on ecosystems, which I know will be of interest to everyone in the Santa Cruz community after the big fires a few years ago. Meanwhile, UCSC has some other exciting events awaiting you might be interested in. It's not too late to join the Deep Read. That's a faculty-led campus-wide book club that's reading the Pulitzer Prize-winning novel Trust by Hernan Diaz. The Deep Read culminates this weekend with a public appearance by the author in conversation with Professor of Literature Zach Zimmer. They'll discuss how the technologies of finance and fiction overlap in his novel about capitalism and its social, cultural, and political power in the United States. It all takes place at Kaiser Permanente Arena on Saturday, May 19th at 4 p.m. Note that that's a change of venue. Also on tap is the second quarterly meeting of Slugs and Scones, maybe our sister event. It's a casual breakfast meetup at UCSC Silicon Valley campus that aims to bring together our Silicon Valley alumni, offering opportunities to expand your local network while providing avenues for continued learning and support. The theme this time is Unlocking Latinx Leadership, featuring UCSC alumnus Ron Gonzalez, graduated from Kresge in '73. He's the current president and CEO of the Hispanic Foundation of Silicon Valley and a former mayor of San Jose. The event aims to spotlight the rich contributions and diverse experiences of our Latinx alumni in Silicon Valley. From groundbreaking innovation to influential leadership roles, our Latinx slugs have been instrumental in shaping the landscape of Silicon Valley and beyond. I'll be there. You can join me on Tuesday, May 21st, from 8 to 10 a.m. at the Silicon Valley campus. On behalf of the UC Santa Cruz Alumni Association, thank you for joining us, and please come back on June 10th, 2024 at 6:30 p.m. for our next virtual event. We'll see you all then.
Thanks, everyone. Good night. Bye.